No fluff, no math, no BS, just data structures. You in. Let's start. Arrays. Imagine a row of lockers at a gym. Each has a number, index, and you can instantly access your stuff if you know the locker number. Arrays store elements contiguously in memory, making access lightning fast. One time. But they're rigid. Adding or removing elements in the middle requires shifting others, which is slow. N time. Perfect for fixed-size datasets where you need frequent random access, like storing high scores in a game or pixel values in an image. Singly linked list of nodes. Each node holds data and a pointer to the next node. Unlike arrays, linked lists can grow, shrink dynamically, and inserting, deleting at the head is quick. Of one time. But finding the 10th node means starting from the first and hopping through each link. N time. Use cases, browser history, back button, or memory management where blocks are scattered. Doubly linked list. Each node links to the next and the previous. This two-way connectivity lets you traverse forward or backward, making operations like deleting the last node efficient one time if you have a tail pointer. It's ideal for apps like music players, skip forward, char, backward, or text editors, undo, redo stacks, where bidirectional movement matters. Circular linked list, a loop playlist where the last song circles back to the first. There's no true end, great for endless cycling, like rotating turns in a multiplayer game or streaming data buffers. Insertions, deletions at the head or tail are one time, but searching still requires traversal n time. Stack. Let's take the classic example of stack of plates. You pick the top one first, last in, first out. Stacks excel at managing function calls, the call stack, syntax parsing, matching brackets, or backtracking, undo operations. Key operations: push, add to top, one time, and pop, remove from top, one time. Searching is slow, n time, but you rarely need it in stack use cases. Queue. A line at an ATM, first person in line gets served first in, first out. Queues handle tasks like print job scheduling, message buffering, or BFS algorithms. NQ adds to the rear, of one time, and DQ removes from front, of one time. Implemented with arrays, fixed size, or linked lists, dynamic. Binary tree. A binary tree is like a normal family tree where each node, person, can have up to 2 children, left and right. No special rules about how values are placed. That's it. It's just a basic structure, great for organizing stuff hierarchically, but not smart about where values go. Binary search tree, BST. A binary search tree is like a binary tree, but with rules. Value of left child is less than the parent. Value of right child is greater than the parent. This rule applies recursively to every node. Why that matters? It makes finding things fast. Searching, inserting, and deleting in BST is O log n if it's balanced. But if the tree gets unbalanced, like inserting sorted data, it turns into a stick, basically a slow linked list. AVL tree. An AVL tree is a self-balancing binary search tree, BST, named after its creators Adelson Velsky and Landis. Yeah, mouthful. It's the first ever self-balancing BST from the 1960s, kinda the OG balanced trees. Every time you insert or delete a node, an AVL tree checks if it's still balanced. If it's not, it fixes itself using rotations. The rule: balance factor. For every node, the balance factor equals the height of the left subtree minus the height of the right subtree. If it's 1, 0, or 1, you're good. If it's less than -1 or more than 1, it's unbalanced, and we fix it with rotations. Types of rotations. To rebalance. 1 LL, left left, do a right rotation. Second RR, right right, do a left rotation. 3 LR, do a left right rotation. 4 RL, right left, do a right left rotation. Red black tree. It's basically a binary search tree, BST, but with a color twist. Each node is painted either red or black. The colors aren't just for style. They enforce rules that keep the tree balanced, so no crazy long branches that slow you down. The strict rules it lives by are: 1. Every node is red or black, simple enough. 2. The root node is always black. 3. Red nodes can't have red children. 4. Every path from a node to its leaf descendants has the same number of black nodes. This is the big one. It means every path is kinda equally heavy in terms of black nodes, so no path gets ridiculously longer. 5. Leaves are black. Segment tree. A segment tree is like a pre-calculated range-based queries, like sum, minimum, or maximum between 2 indexes. It's built in O of n time by recursively splitting the array into segments and storing those results in a tree. When you need to update a value, you don't have to redo everything. You only fix the segments affected, which takes O log n. That's what makes it a go-to tool in problems like stock price analysis or image processing. Try. Each level represents a letter of a word, so if you store words like cat and car, they'll share the path for C and A before splitting into different branches. This clever structure makes it insanely fast to search for words, with time complexity depending only on the word length, O, M. That's why tries power things like autocomplete systems, spell checkers, and even routing tables for IP addresses. They shine when you have to manage millions of words or prefixes, but still need lightning-fast lookups. Heap. A heap is like a pyramid of priorities. In a min heap, the smallest element bubbles up to the top. A max heap, on the other hand, keeps the largest element at the top, handy when you need quick access to the biggest value. Heaps are implemented as arrays, and parent-child positions are figured out using simple index math. Both insertions and extractions take O log n, making heaps crucial in algorithms like Dijkstra's, or even in building an efficient heap sort. Priority queue. Think an emergency room where the most critical patients get seen first. Unlike regular queues, it doesn't follow first come, first served. Instead, it pulls out the highest priority item every time, whether that's the smallest or largest based on your setup. It's usually built using a heap under the hood to keep things efficient, with operations like insert and remove staying at O log n. You'll find priority queues everywhere: real-time systems, operating system schedulers, network packet routing, and anywhere else where urgency decides who goes next. Graph representations. Adjacency matrix. Imagine a chessboard where each square represents a potential connection between two nodes. In an adjacency matrix, nodes are labeled from 0 to n-1, and the matrix is a two-dimensional grid of size n by n. If there's an edge between node I and node j, the cell ij is marked 1, or the edge weight for weighted graphs. If no edge exists, it's 0. Adjacency list. Think of a phone contact list where each person, node, has a list of friends, neighbors. In an adjacency list, each node points to a dynamic collection, like an array or linked list, of its directly connected nodes. Hash table. A hash table is a data structure that lets you store and retrieve values in near instant time, on average, by converting keys like usernames, IDs, or words into unique addresses in memory. Every hash table starts with a hash function, a mathematical algorithm that takes a key and scrambles it into an index, a position in an underlying array. Example, for a key XYZ, the hash function might compute index imshears 3, pointing to slot 3 in the array. Handling collisions, the bouncers. When two keys hash to the same index, the hash table uses one of two strategies. A. Chaining. Each array slot holds a linked list, or another structure. Colliding keys are added to the list at that index. B. Open addressing. If a slot is occupied, the table probes for the next empty slot using methods like linear probing, check index +1, index +2, etc. Double hashing. Use a second hash function to calculate the step size. That's it for today's video. Thanks for watching.